Have you ever wondered how organic compounds are classified? Well, you're about to find out. Organic compounds are primarily made up of carbon atoms. But what makes them truly interesting is the variety of other elements they can contain and the functional groups they can form. Consider this: an organic compound could be as simple as a hydrocarbon, containing only carbon and hydrogen atoms. These include alkenes, alkynes, and more. But then, we can add oxygen into the mix, and we get alcohols, phenols, and esters, among others. We can further extend this by introducing nitrogen, creating amines and imines, or even halogens, leading to alkyl and aryl halides. And let's not forget about those that contain sulfur, which gives us sulfonic acids and sulfonyl halides. Imagine the vast diversity created by these combinations. It's a complex and intriguing system, isn't it? Stick around to understand the fascinating world of organic compounds. Imagine a world with just carbon and hydrogen. What do you get? Hydrocarbons. In the realm of organic chemistry, hydrocarbons are the simplest of compounds, composed only of carbon and hydrogen atoms. Despite their simplicity, they come in a variety of types, each with its own unique properties and applications. First up, we have alkanes. These are the most basic type of hydrocarbon, where each carbon atom is bonded to the next with a single bond. Picture a chain, with each link representing a carbon atom, and you have got the idea. Then come the alkenes. These are a little more interesting because they contain a double bond between two carbon atoms. This double bond gives alkenes more reactivity compared to alkenes. It's like having a two-lane highway instead of a single lane. More lanes, more action. Next, we have alkynes, the rebels of the hydrocarbon family. Alkenes contain a triple bond between two carbon atoms, making them even more reactive. It's like having a three-lane highway now. More lanes, even more action. And then there are the aromatic hydrocarbons, the celebrities of the hydrocarbon world. They're composed of cyclic molecules with alternating single and double bonds, creating a stable and unique structure. Think of them as the VIP lounge of hydrocarbons, where every atom has a special place. We also have aryl-alkyl hydrocarbons, which are a combination of aromatic and aliphatic hydrocarbons. Picture a VIP lounge with an extension to the regular area. That's your aryl-alkyl hydrocarbon. Lastly, we have the alicyclic hydrocarbons. They are cyclic like the aromatics, but without the alternating single and double bonds. They're like the quiet cousins who still have their own charm. Despite their simplicity, hydrocarbons play a significant role in our daily lives. They're in the fuel we use for our cars, the plastic products we use each day, and even in the medicines that keep us healthy. And that's just the tip of the iceberg. There's more to come. Now let's add a pinch of oxygen into the mix. When we introduce oxygen to carbon and hydrogen, we open up a whole new world of organic compounds. This trio of elements forms the basis for a vast array of molecules that are critical to life as we know it. First up, we have alcohols. Picture the most basic alcohol, methanol. It's a simple molecule with a single carbon atom, 4 hydrogen atoms, and, here's the key, an oxygen atom linked to a hydrogen atom, forming what we call a hydroxyl group. And it's this hydroxyl group that makes it an alcohol. Now let's move on to phenols. Similar to alcohols, phenols also contain a hydroxyl group. But here's the difference. The hydroxyl group in phenols is directly bonded to a carbon atom within an aromatic ring, a hexagonal ring of carbon atoms, like in benzene. Then we have ethers and epoxides. In ethers, an oxygen atom is sandwiched between two carbon atoms. In epoxides, an oxygen atom is part of a 3-membered ring, which also includes 2 carbon atoms. Next in line, we have carbonyl compounds, which include a wide variety of substances like aldehydes, ketones, and more. The carbonyl group, consisting of a carbon atom double bonded to an oxygen atom, is what defines these compounds. We also can't forget about carboxylic acids, esters, and anhydrides. Each of these contains a carbonyl group, but with a twist. Carboxylic acids have a hydroxyl group attached to the carbonyl carbon. Esters have an oxygen atom linking the carbonyl group to another carbon atom. And anhydrides? They have 2 carbonyl groups separated by an oxygen atom. So, you see, this trio of carbon, hydrogen, and oxygen brings a wealth of diversity to the world of organic chemistry. Each combination, each arrangement of these three elements results in entirely different compounds, each with their own unique properties and uses. Oxygen surely brings life to more than just humans, doesn't it? What happens when nitrogen joins the party? Imagine our chemical soirée, the atoms all mingling, suddenly enriched by the arrival of nitrogen. This element, the party crasher, certainly shakes things up, adding a whole new layer of complexity to our organic compounds. Let's start with amines and imines. Amines are organic compounds where one or more hydrogen atoms in ammonia are replaced by an organic group. They play a crucial role in the creation of proteins, which are fundamental building blocks of life. On the other hand, we have imines, a class of compounds featuring a carbon-nitrogen double bond. They might not be as well known as amines, but they're vital in the production of many pharmaceuticals. Moving on, we encounter nitriles. These compounds are characterized by a carbon-nitrogen triple bond. Nitriles might sound exotic, but they're actually quite commonplace. They're used extensively in the production of synthetic fibers, like those in your easy care, wrinkle-resistant clothing. Next, we meet hydrazines. These are compounds with two nitrogen atoms bonded together, with hydrogen atoms surrounding them. Hydrazines are incredibly reactive, which makes them perfect as rocket fuel. Quite literally, they're used to propel us to the stars. Finally, we have nitro compounds. These are organic molecules that contain one or more nitrofunctional groups. They're quite the firecrackers, often used in the production of explosives, yet they also have a more peaceful application in the creation of dyes and polymers. So when nitrogen crashes the party, it doesn't just stand in the corner. It dances with carbon and hydrogen, forming compounds that are essential to life, industry, and even space exploration. It helps create the proteins we need, the clothes we wear, the medicine we take, and the rockets that propel us into space. It's safe to say, things are never dull when nitrogen joins the party. And there you have it. Nitrogen, the party crasher, certainly makes things interesting. We'll continue our journey into the world of organic compounds in the next segment. Stay tuned. Ever wondered about the role of halogens in organic compounds? Well, let's dive in. Halogens are the group 7 elements on the periodic table, and when they join the organic party, things get really interesting. Consider compounds like alkyl halides, which are simply hydrocarbons where one or more hydrogen atoms have been replaced by a halogen. These compounds are incredibly versatile and are used in a wide range of chemical reactions. Then we have aryl halides, where a halogen is directly bonded to a carbon atom of an aromatic ring. They play a crucial role in the synthesis of many pharmaceuticals and dyes. Lastly, let's not forget acyl halides. These are derived from carboxylic acids by replacing a hydroxyl group with a halogen. Acyl halides are highly reactive and are primarily used in the production of other acyl compounds. Sure do make a splash in organic chemistry. Now, let's mix things up a bit. With the addition of multiple elements, the complexity and diversity of organic compounds increases exponentially. This is where we encounter compounds that not only contain carbon, hydrogen and oxygen, but also nitrogen. Examples of these include amidase, imides, aldoxime, and ketoxime. Each of these compounds showcases unique chemical properties and behaviors due to their distinct elemental composition. But why stop there? Let's add sulfur into the mix, bringing us to compounds like sulfonic acids and sulfonyl halides. These concoctions contain carbon, hydrogen, and sulfur, but they don't shy away from including nitrogen, oxygen, or halogens either. The inclusion of these elements creates a new level of complexity, leading to a fascinating array of chemical interactions and reactions. In the grand scheme of things, it's all about the elemental composition. The unique blend of elements in each compound dictates its properties and potential applications. As they say, the more the elements, the merrier the compounds. It's been quite a journey, hasn't it? We've journeyed together through the fascinating world of organic compounds. From the simplest, like hydrocarbons, composed of merely carbon and hydrogen, to the more complex, incorporating elements such as oxygen, nitrogen, halogens, and sulfur. We've explored how these elements come together to form an array of functional groups, each with unique properties and reactions. We delved into the realm of alkenes and alkynes, the alcohols, phenols, and ethers, and even the intricate world of carbonyl compounds and carboxylic acids. We've discovered how nitrogen transforms simple hydrocarbons into amines and imines, and how halogens create a new dimension within organic compounds. We've even touched upon the multifaceted compounds containing multiple elements, like sulfonic acids and sulfonyl halides. It's an intricate dance of elements and compounds, each with its own rhythm and pattern. So let's keep exploring, keep asking, keep learning. Subscribe for more mind-blowing insights into the world of chemistry.